Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Engineering and Technology, SOET, Bachelor of Science, Applied Science Energy, BSc. Semester I. BEY-01 to Electrical and Electronic Sciences. Block 1 Basic Electrical, I. Unit 1 Introduction to Electricity. 1.1 Introduction. Electricity is the most conventional form of energy and has multiple applications like lighting, communication, heating, transportation, air conditioning, etc. The flow of electricity can be compared with the flow of water in a pipe. Flowing water is a good analogy of electricity. When water flows through a pipe or downstream, there is a water current. Similarly, electric current or simply current is the flow of electrons in an electric circuit. The flow of current depends upon amount of charge or the number of electrons flowing. If we have to measure how fast the water is flowing in a pipe, we may say it is so many gallons per minute. When we measure how much current is flowing through a wire, it is based on the number of electrons flowing past that cross-section of wire in 1 second. There is a unit of measure called the coulomb, which enables us to measure the amount of charge in an object, e.g., an electron. Since there are billions of electrons flowing through the wire, we instead measure the charge with unit coulomb, which is 6.24 billion electrons flowing through the wire to measure electric current. Ampere is the basic unit of electric current. When 1 coulomb of electrons passes through a wire in 1 second, we say that there is 1 ampere of current. It is sometimes referred to as amps. Hence, I is equal to charge time, I is equal to dq dt. Water flows through a pipe because of water pressure. Water pressure forces the water to flow. Likewise, electromotive force, EMF, is the pressure that forces electrons to flow through a circuit. Electromotive force is also known as voltage. The basic unit of electromotive force is volt. In the same fashion as water flows down in the stream, through a pipe, current can flow in a circuit. Water is limited by the amount of friction it encounters as it flows. Electricity is limited by the amount of resistance it meets as it passes through a circuit. Resistance limits the current that flows through a circuit for a particular applied voltage. Hence, resistance acts as a friction in flow of current. However, if we increase the water pressure in a pipe, more water would flow. Similarly, if we turn up the voltage, then more current would flow. The material or the medium plays an important role. There are some materials in which electricity flows easily. These materials, thus, have very low or negligible resistance and are called conductors. Most metals are conductors. 3 good electrical conductors are gold, silver and aluminum. Insulators are materials that do not let electricity flow through them and, thus, have very high or almost infinite resistance. 4 good insulators are glass, air, plastic and porcelain. In this unit, basics of electricity like charge, potential difference, resistance and Ohm's laws are discussed with the application and working of batteries. Objectives. After studying this unit, you should be able to explain the laws of electricity, evaluate the combination of series and parallel resistors and capacitors, including Kirchhoff's laws, describe different types of cells and batteries, and explain the distribution of electricity. 1.2 Electricity. Every engineer is directly or indirectly concerned with the applications of electricity. Thus, a civil engineer requires some basic knowledge of electric motors, which are being widely used in the modern construction machinery. Applications of electricity. In the modern world, dependence on electricity is unavoidable. The ever Increasing importance of electricity is due to its numerous applications for domestic and industrial purposes. A few important applications of electricity are discussed below. Heating. One of the important applications of electricity is its use for heating purposes in the domestic and industrial field. In all electric heating appliances, electrical energy is converted into heat by passing an electric current through a wire of high resistance. Domestic applications: electric press, heater, coffee percolator, toaster, electric kettle, etc. Industrial applications: electric ovens, electric furnaces, etc. Lighting. The other important application of electricity is its use for lighting purposes. In all such devices, electrical energy is converted into light energy by utilizing the effects of electricity. Domestic applications: electric bulbs, fluorescent tubes, discharge lamps, sodium lamp, mercury lamp, etc. Industrial applications: all domestic lighting devices and lamps for cinema, projectors, etc. Electric motors. The main application of electricity is its use for running electric motors. In all electric motors, electrical energy is converted into mechanical energy. Domestic applications: hair dryer, mixer, refrigerators, ceiling and table fans, air cooler, washing machine, etc. Industrial applications: lifts, cranes, tube wells, concrete mixer, lathes, etc. Electroplating. Electricity is used for the process of electroplating, i.e., coating a layer of superior metal over inferior metal. Domestic applications: tin plating of utensils, etc. Industrial application: nickel plating of vehicles, watch cases, etc. Electronics. All electronic devices require electricity for running the devices. Advantages of electricity. We have explored electricity about numerous domestic and industrial applications. Electrical energy has virtually established its superiority over other forms of energy. There are a number of reasons for preferring electrical energy over other forms of energy. Convenient form. It is a very convenient form of energy. It can be easily converted into other forms of energy. For example, if we want to convert electrical energy into heat energy, then electric current is passed through a wire of high resistance. Easy in handling. Electricity can be very easily handled. Wherever it is required, it can be taken with the help of conductors, copper or aluminum wires, and, thus, can be used for various purposes. Low cost. Low cost is another factor which goes in favor of electricity for its wide use. Electrical energy can be easily and cheaply produced. No fumes or poisonous gases. The use of electrical energy is not associated with smoke, fumes or other poisonous gases. Therefore, it can be safely used for domestic and industrial purposes. Cleanliness. It is a very clean form of energy as compared to other forms of energy. As already explained, electricity is free from smoke, fumes or poisonous gases. Therefore, its use for domestic and industrial purposes is on the increase. More efficient. Electric appliances are very efficient and, therefore, they are fast replacing manual labor. Easy transportation. Electricity is perhaps the only form of energy which can be transported very easily and with very high efficiency over distances as long as few thousand kilometers. 1.3 Current. 1.3.1 Free electron theory. As we are aware, the atom is most fundamental unit of matter. Generally, according to atomic structure, the atom consists of a nucleus and electrons. All electrons move around the nucleus in different orbits or shells. These orbits are energy levels. The electrons present in the outermost orbit are called valence. Electrons in modern physics, and the valence electrons that are able to move from one atom to another atom in a random manner, are known as free electrons. Free electrons, thus, work as charge carriers and can carry charge from one point to another point when an external field is applied. According to energy band theory, the forbidden energy gap is absent between valence and conduction band in good conductors. Thus metals, which work as good conductors, contain large number of free electrons at normal temperature without supplying any additional energy. Materials which are bad conductors possessing a higher energy gap between the valence and conduction bands are called insulators. 1.3.2 EMF and current. In the study of an atomic structure, a neutral atom contains equal number of protons in the nucleus and electrons in the shells. Protons are positively charged particles and electrons contain negative charge. Normally, an atom loses an electron when it becomes positively charged or positive ion. Similarly, after gaining an additional electron, the atom becomes negatively charged and is known as negative ion. The ability of two oppositely charged bodies to produce a flow of electricity between them is the potential for the production of electric current. Thus, a positively charged body is said to be at positive potential and a plus sign is used to identify this potential. Similarly, a negatively charged body is described at negative potential and a sign is used to identify this potential. The arithmetic difference between the two is called potential difference between them. It is measured in volts, V, and a term, voltage, is applied for potential difference. The magnitude of potential difference between 2 points is equal to the work done in moving a unit positive charge from one point to another. In electrical circuits, potential difference is provided by some external means like a cell or a battery. A cell or battery provides an electrical potential that tends to cause current to flow. It is also known as electromotive force, EMF, and is measured in volts. When a suitable conductivity path or good conductor is used, then a current will flow as a result of electric pressure. The current flows from positive potential to negative potential. But actually the direction of flow of electrons is towards positive potential from negative potential and may be considered as flow of equivalent positive charge in the opposite direction as shown in figure 1.1. Conventionally, the current produced by flow of electrons is supposed to be the flow of plus V charge and, thus, flows from positive potential to negative potential. See, unit of current is ampere, A, and its symbol is I. Figure 1.1, electron flow. Look at the screen. Current that flows continuously in one direction is known as direct current. DC, direct current is supplied by voltage cell because the polarities of voltage cell do not reverse with passage of time. Thus, a voltage cell is termed as direct voltage source, DC voltage source, as shown in figure 1.2. Figure 1.2, direct and alternating voltage source. Alternating current, AC, is the current that flows first in one direction for a small time and then reverses the flow in the opposite direction for a similar time. Voltage source capable of producing alternating current is called alternating voltage source or AC voltage source. 1.3.3 Ohm's law. The opposition to current flow that exists in every material is called resistance. It is the property of material by which we know how it resists flow of current. The property which supports flow of current is known as conductance. The reciprocal of resistance, R, symbol for a resistor, is conductance, G. The resistance is measured in ohms, omega. The conductance is given as Conductance, G is equal to 1 upon resistance is equal to 1 by R. Siemens, S, is the unit of conductance. According to Ohm's law, the current, I, flows through a resistor due to electric pressure and is directly proportional to the magnitude of electrical pressure, V. Therefore, current is equal to voltage upon resistance. Therefore, I is equal to V by R. The resistance of a resistor depends on area, length and resistivity of material of resistor and is given by R is equal to PL by A. Here, ρ is equal to resistivity, L is equal to length of resistor, and A is equal to area of cross-section. Resistivity is the property of material and depends upon the internal structure of a metal or a conductor. It is measured in ohm or ohm cm. 1.3.4 Effects of electric current. When an electric current flows in a conductor, heat is dissipated as a result of work done in moving electrons. For example, work is performed in a lamp filament when the electric current is converted into light. The power, P, is the rate of doing work. If work done is W, then power is equal to Wt. The C unit of power is joules second, Js, termed as watt, W. In a resistance, heat is produced by flow of current due to work done in moving charge Q across potential V, which is given by W is equal to V into Q. This, power Wt is equal to V into Qt is equal to V into L is equal to voltage into current. Therefore, P is equal to into L is equal to it not I using Ohm's law. The unit of electrical power is watt, W, or kilowatt, kW. This power is wasted in electronic circuits, but in order to protect the equipment, fuses are used. Fuses are designed in such a way that the current flow exceeds the design limit. The power is dissipated in fuse to cause it to melt and blow off to protect a device by interrupting the current flow in the circuit. The electrical appliances are rated in W or kW consumed energy. Thus, the energy is the consumption of power in a specified time. W is equal to PT. Its C unit is kWh and is measured by energy meters. 1.4 Resistance of a conductor. 1.4.1 Resistance of resistors in series. Resistors are said to be in series when they are connected in such a way that there is only one path through which current can flow, figure 1.4. This means current in a series circuit is the same in all parts of the circuit. The voltage drop across each component in a series circuit depends on the current level and the component resistance. 1.4.2 Resistance of resistors in parallel. Resistors are said to be connected in parallel when the same voltage appears across each component with different current flows through each resistor. The total current flow into and out of parallel combination is the sum of all the individual resistor currents as shown in figure 1.6. Figure 1.6, Parallel resistance. Look at the screen. Two resistors connected in parallel may be used as a current divider. The voltage V appears across each resistor. Thus, we see that two parallel connected resistors functioned as a current divider. 1.4.3 Series and parallel combination of resistors. Generally, most of the circuits have series and parallel combinations. The simplest approach to analyze a series parallel circuit is to resolve each purely series or purely parallel group into its single equivalent resistance till we arrive at a single equivalent resistance across voltage source. Figure 1.8, A, combination of series and parallel. Look at the screen. 1.5 Kirchhoff's laws. These laws are more comprehensive than Ohm's law and are used in solving the electrical circuits which may not be solved by the latter. 1.5.1 Kirchhoff's current law, KCL. In any circuit, the algebraic sum of all the currents meeting at a point is zero. The total current leaving a junction or point is equal to total current entering that junction. It proves conservation of charge as charge is not stored at a point. And the charge entering a point has to be equal to charge leaving that point, i.e. sigma I is equal to 0 at a point or junction, as shown in Figure 1.10. Look at the screen. Figure 1.10, Kirchhoff's current law. Here, I enters at junction and I1, I2 and I3 are leaving the junction. Assuming incoming currents plus V and outgoing currents as V, we have algebraic sum of currents meeting at junction A as I1, I2, I3 is equal to 0. Or I1 plus I2 plus I3 is equal to 0. I.e. I is equal to I1 plus I2 plus I3. Thus, KCL also implies that sum of incoming currents equals sum of outgoing current. 1.5.2 Kirchhoff's voltage law, KVL. In any closed circuit, the algebraic sum of the voltages reckoned in a particular direction is 0. Conventionally, voltage drop in the direction of traversal is taken as negative, while a rise in voltage is taken as positive. It may be remembered that across a resistor voltage drops in the direction of current, while it rises in the opposite direction, as shown in Figure 1.11. Thus, sigma V is equal to 0 round a mesh or path. In a closed circuit ABDA, in the clockwise direction the voltage drops are I1, R1, I2, R2, I3, R3, I4, R4 and V2 while the voltage rise is V2. In a path ABDA, considering a rise in voltage is positive and fall in voltage is negative. The polarity of voltage drop appears across any resistor. Thus, KVL also means that in a closed circuit total voltage drop across resistors is equal to algebraic sum of voltage sources reckoned in the direction of voltage drops across resistors. In a closed circuit, if there is no source of EMF, then sum of voltage drops is equal to 0. 1.6 Batteries. A battery is a collection of two or more than two cells. A cell is the smallest unit of a battery, which converts chemical energy to electrical energy. A cell always gives DC voltage, EMF, and DC current. Cells are of two kinds: primary cell and secondary cell. Primary cell. A cell based on irreversible reactions, whose components must be renewed, or the cell itself be replaced when it is run down, is known as a primary cell, e.g. simple voltaic cell, Daniell cell, Leclanché cell and dry cell. Secondary cell. A cell based on reversible reactions, whose components, i.e. electrodes and electrolytes, can be brought back to normal state by passing a current through it in the opposite direction, is known as a secondary cell, e.g. lead acid cell, nickel alkaline cell. Look at the screen. Figure 1.16, Different types of cell. 1.6.1 Construction of lead acid battery. Positive and negative plates. Figure 1.17, Types of lead acid accumulator. Separators. They are used for insulating the negative and positive plates. They are made of thin sheets of perforated hard rubber or plastic material of fiberglass or wood. Electrolyte. Diluted sulfuric acid fills the cell compartment to immerse the plates completely. Container. Battery parts are placed within the container and protected. Partition walls are provided in the container for cells. Bottom blocks. The bottom grooved support blocks are placed at the bottom of the container, which converts the active materials which fall from plates. In this way, it prevents the short-circuiting of the plates. Plate connector. It is a lead plate which is assembled to a group of positive plates or to a group of negative plates. An upward connection of the plate connector forms a Terminal of a cell. Cell connector. Various cells constitute a battery. The negative terminal of one cell is arranged close to the positive terminal of the next cell and connected together so that the cells can be connected in series. These connectors are either of pure lead or of a special lead alloy. Terminal posts. They are the upward extension of the two extreme plate connectors. The connections for outside circuit are taken from these terminal posts. They are marked plus V or V. Vent plug or filler caps. These are made of rubber or polystyrene and screwed to the cover of the cell. Their function is to prevent escape of electrolyte but allow free exit of gases. External connecting straps. These are the antimony lead alloy flat bars which connect the positive terminal post of one cell to the negative of the next across the top of the cover. These are of very solid construction, especially in starting batteries because they have to carry very heavy currents. Active materials of a lead cell. The active materials of a lead acid accumulator are PbO2, lead peroxide. It is a chocolate brown colored, hard and brittle rod, which forms the positive plate of the battery. Pb, sponge lead. It is pure lead in soft sponge or porous condition. It forms the negative plate of the battery. Dilute H2SO4, dilute sulfuric acid. Concentrated H2SO4 of specific gravity 1.84 is taken. 1 part of it is mixed with 3 parts of distilled water to prepare a diluted sulfuric acid of specific gravity 1.24. Thus, the lead acid accumulator depends for its action in the presence of 2 plates of PbPbO2 in a solution of diluted sulfuric acid of specific gravity 1.21 to 1.24 or near about 1.6.2 chemical reactions. Charging and discharging of lead acid batteries. In the process of manufacturing of cells, the plates are in the charged condition. In the charged condition, positive plate or anode consists of lead peroxide PbO2, dark chocolate brown, and the negative plates or cathode is in lead, Pb, slate gray. During charging, the following reactions occur. PbSO4 plus H to Pb plus H2SO4. At cathode, PbSO4 plus SO4 plus 2H2O PbO2 plus 2H2SO4. At anode, at the end of charging, i.e. fully charged, anode becomes PbO2. Color, chocolate brown. 2. Cathode becomes Pb, color, slate gray. 3. Density of electrolyte, i.e. its specific gravity becomes 1.23 to 1.28. 4. Approximate value of EMF is 2.3 volts. V. Cell stores energy. B. During discharging, the following reactions occur. PbO2 plus H2 plus H2SO4 PbSO4 plus 2H2O at anode. Pb plus SO4 PbSO4 at cathode. During discharging, both anode and cathode become PbSO4, which is whitish in color. 2. Due to formation of water in the anode reaction, the specific gravity of the electrolyte decreases and may even reach as low as 1.15 or 1.05. 3. Voltage, EMF, of the cell decreases. 4. Cell gives out energy. Single reaction. PbO 2 plus 2H 2 SO 4 plus Pb PbSO 4 plus 2H 2 O plus PbSO 4 plus V electrolyte V plus V water V plate. Initial charging. Charging a new battery for the first time is called initial charging. Steps. A. Battery is cleaned. B. Electrolyte of specific gravity P is equal to 1.23 is provided. C. Battery is allowed to cool for 14 to 16 days. D. Level of electrolyte, which decreases, is again brought back to the level by pouring more of it and again cooling for 3 to 6 days. E. Initial charging is done at a rate lower than the normal. F. At the end of charging, i.e. after 2 to 3 days, the P is adjusted by adding distilled water. Thereafter, the battery is discharged at a rate lower than normal for the first 1 or 2 times. The battery is put to the normal service after charging and discharging. 1.6.3 Testing of lead-acid battery. To know the latest charged position, testing of battery is done by measuring the specific gravity of electrolyte and the voltage with a cell tester. For a fully charged battery, the voltage of each cell should be about 2V to 2.07 V, while the specific gravity should be about 1.26. 1.6.4 Care and maintenance of lead-acid battery. There are some important points, as listed below, which help in care and maintenance of battery like G. Lead-acid batteries should be brought up to full charge at the earliest. Avoid continuously operating batteries in a partially charged condition. This will shorten their life and reduce their capacity. H. Inactivity can be extremely harmful. I. When not in use, remove electrical connections from the battery, including series parallel connectors. J. Store battery in a cool place. K. Extreme temperatures can substantially affect battery performance and charging. L. Batteries should be kept clean, free of dirt and corrosion at all times. M. New batteries should be charged properly. 1.6.5 Trickling charge. Under idle condition, the battery discharges very slowly due to self-leakage. 2. Keep the battery fully charged under critical operating conditions, it is continuously charged at the same rate as that of discharge. This slow charging of battery is called trickle charging. Thus, when the battery is charged at a very low rate, i.e. about 2 to 3% of the normal rate for a long time, then it is said to be under trickling charge. In electrical power substations, where these batteries are the heart of the system, trickling charge is used. 1.6.6 Advantages of storage battery. A. Storing of energy in the battery can be done at any convenient rate, but may be delivered at any other rate. B. It is the most efficient device for supplying of electrical energy in a portable form. C. Energy stored in the battery is available immediately without any lag of time. 1.6.7 Applications of lead-acid battery. In electrical power stations and substations, relays are operated by supplying electrical energy by the lead-acid batteries. 120 such batteries of 2V each are connected in series to give 240 V. Other applications of lead-acid batteries are as follows. A. Emergency light and fans, inverters etc. B. Cars, trucks, jeeps etc. C. Industries and mining. D. Ships and submarines. E. Standby power supply for telephone exchange, radio stations, etc. 1.7 Summary. After going through this unit, you should have understood the effects of electricity and also the properties of resistors and capacitors. You would also have a general understanding of Kirchhoff's laws, Ohm's law and principles of batteries operation. Thank you for watching. We will see you in the next video with the next chapter.